Have you ever looked at a complex engineering drawing and wondered how all those lines and symbols become, well, real? How they transform into the powerful, reliable, beating heart of our electrical grid? Well, today we're pulling back the curtain on that final, critical step. We're going to dive deep into the world of high-voltage substation commissioning, the process that turns a construction site into a live power hub. So what is commissioning, really? Think of it as the ultimate final exam for a brand new substation. It's this incredibly thorough series of checks and tests that guarantees every single component, every wire, and every line of code is absolutely ready to do its job safely and reliably, right from the moment it goes live.
You see, it all boils down to these key goals. This is so much more than just flipping a switch. It's about verifying every piece of equipment against tough global standards. It's about making sure the safety logic will react in milliseconds to protect the grid. And of course, it's about confirming the operators can see and control everything remotely, while hunting down and fixing every last potential defect. This is what turns a bunch of expensive hardware into one cohesive, intelligent system.
Now, to make all this work, everyone, and I mean everyone, has to be on the same page, following the same rulebook. That rulebook comes from the International Electrotechnical Commission, or IEC. You can think of these standards as the non-negotiable foundation, the global language that governs how every single piece of equipment in that substation is designed, built, and tested. Okay, let's talk about the heavy hitters, the primary equipment that's handling immense amounts of power. You've got the gas-insulated switchgear, which safely contains high voltage in a really compact space. You have the giant power transformers that step that voltage down. And then you have the circuit breakers. These are like giant, super-fast switches that can stop a fault dead in its tracks. Each one has its own specific IEC standard to make sure it performs perfectly, especially under pressure. But, it's not just about raw power. It's also about intelligence and control. This here is the substation's nervous system. We have standards for the current and voltage transformers. Those are the senses of the substation. And for its brain, the substation automation system, or SAS. And that whole control network is governed by a real game changer, the IEC 61850 standard. We'll be talking more about that one in just a bit. Right, before even a single volt of electricity gets applied, the groundwork has to be absolutely perfect. This is the pre-commissioning phase. It's a hands-on, physical check of every nut, every bolt, every connection. It's all about making sure the physical construction perfectly matches the engineering design down to the last detail. And the key here is just painstaking attention to detail. Engineers are out there physically inspecting everything for damage. They're using torque wrenches on every connection because a single loose bolt can lead to a catastrophic failure. They test cable insulation, check for tiny leaks in the SF6 gas that prevents sparks, purify the transformer oil. They even verify the entire station's safety ground grid. Nothing, and I mean nothing, is left to chance. Okay, with all the physical checks done, we move into the electrical testing. This is where we start using specialized test equipment to energize individual circuits. We're not just validating that each device works, but more importantly, we're making sure they all work together as one single integrated system. A great way to think about this is muscles versus the nervous system. The primary tests on the left, those check the high voltage muscles to make sure they can handle the power. The secondary tests on the right, that's all about the nervous system, the protection relays and control logic. We're making sure the brain is giving the right commands at exactly the right time. And at the very heart of that nervous system is IEC 61850. Now, this isn't just another standard. It's the digital backbone of any modern substation. It's what allows all the smart devices, or IEDs, from totally different manufacturers to talk to each other over a network. They're all speaking the same digital language for unbelievably fast and reliable protection. This is where the real digital magic happens. Engineers test these critical signals called goose messages. Think of them as urgent digital signals that fly across the network in just a few milliseconds to tell a circuit breaker to trip during a fault. They also test safety interlocks to prevent dangerous mistakes, confirm everything can be seen and controlled from the main control center, and map out every possible alarm. And now, for the moment everyone has been working towards, energization. This is the climax of the entire project, where the substation is carefully, methodically brought online for the very first time. And trust me, it's not a single event. It's a highly controlled, systematic sequence. Following this sequence is absolutely critical for safety. First, engineers make sure the new substation is perfectly in sync with the wider grid. Then, they energize the main bus bars.
After that, the power transformers come online. Then, one by one, the outgoing power lines, or feeders, are brought to life. And finally, as the station starts taking on load, the whole system is monitored like a hawk for stability. Once the substation is energized and running stable, there's one last crucial step. This is the formal handover. It's where the commissioning team documents every single test and every result before officially transferring ownership of this brand new asset to the operations team, the folks who will run it for decades to come. This handover package is basically the substation's official birth certificate and its complete medical history, all rolled into one. It has all the test results, the final as-built drawings showing exactly how it was constructed, the critical protection settings files, and of course the official certificate approving the energization. It's the definitive record of the entire project. So, there you have it. From a simple blueprint, a collection of steel, copper, and silicon has been safely transformed into a living, breathing node of the power grid. But this leaves us with a fascinating question for the future. How will technologies like AI and fully detailed digital twins, I'm talking virtual replicas of this entire substation, change how we test and commission the next one? Now that's a thought to power us forward.